Okay, we're going to talk about linear functions, and we're going to again talk about the constant rate of change that we just were talking about, because linear functions have a constant rate of change, which is our slope. We're going to construct linear models. We're going to again talk about slope, which is m is delta y over delta x. And we're going to find formulas for linear functions from tables of data, graphs, and we're going to also use words. Okay, so the first one is a really good problem. Search and rescue teams work to find lost hikers in remote areas. To search, members of the search team separate and walk parallel to each other. Experience has shown that the team's chance to find a lost person is related to the distance by which the teams were separated with the percent found. So here we have a table here. I have distance found, we'll call this x, and the percent found we'll call y. Now this is dependent on this because if you'll notice, as the distance between the walkers walk, so they're like in a line here, and if they are 20 feet apart, they have a 90% chance of finding the lost person. If they split up more and more, or less searchers are there, the percentage goes down to find the child or whoever's lost. Okay? So first of all, how can we tell from the table that it's a linear function? Well, here is where you're going to use the carets again. So we're going to do the caret here, so I increase 20 here, increase 20 here, increase 20 here, and increase 20 here. So this is a constant. That's a good sign. And then here I went from 90 to 80, so that dropped 10, drop 10, drop 10, drop 10. So how can we tell from looking at the table? Well, we have a constant rate of change. Okay, how can we find what this constant rate of change is, or the slope? Well, slope, again, is delta y over delta x. And since this is my y, the change in y is actually negative 10 over the change in the x's, or 20, or negative 1/2. And it's constant all the way. You can see it here, here, here. It's constant the whole way. Now, if we give the meaning of the slope, I showed you here, is delta y over delta x. And this is your rate of change. All right? So let's practice some with some other tables, and we'll check to see if they're linear. And the best thing to do these is to show your carets. But you don't want to get tricked up because sometimes they don't go in order. So let's do our carets here. So I'm increasing 1, increasing 1, increasing 1. Here I'm going up 7. It's 7, sorry. Increasing 7, increasing 7. So is this linear? Yes, it is. It has a constant rate of change. What is our slope? Well, it's 7 over 1 each time, or 7. So that is a linear function. Let's look at the second table. Let's do our carets for that. I've increased 1, increased 1, increased 1, so that's constant. Let's look here. I went up 3, up 4, up 5. Now, if this is constant and I'm doing my rate of change, look at my slopes. It's going 3 to over 1, to 4 over 1, to 5 over 1. So it's getting progressively steeper or increasing faster and faster. This is not linear. So no, this is not. Now, here's where the tricky part comes. Because this one, if I look at it really quickly, I say, okay, this is going up 2, this is going up 3, and this is going up 4. So there's my delta x's. I've got them here. And you can look right at it and say, no, it's not. Well, you got to be careful, because when you look at this down here, I see this has dropped 4, dropped 6, and dropped 8. You're like, it's definitely not linear. But let's do our slopes. Slopes are delta y over delta x. So let's look at it. My delta y here is negative 4 over 2. My delta y here is negative 6 over 3. My delta y over delta x is negative 8 over 4. Aren't they all negative 2? So yes, this one is definitely linear. You just have to be careful because sometimes they don't pick all the points right in a row. Okay, so let's talk more about the formula for linear functions, and that's y equals b plus mx. Now I know a lot of you are used to hearing mx plus b. I like to have the b first because the b stands for my y-intercept, and if you're doing life in quadrant 1 like we've learned, usually if this is my linear function, I'll pick an increasing one. This is my b, or my y-intercept, that's your beginning. So it's a nice way to do the problem. So I always like to put the y-intercept first. The m, of course, stands for slope. And slope, again, is delta y over delta x. All right. It has a constant rate of change, linear functions do, which we've talked about. And the graph of any linear function is a straight line, because the rate of change is constant. Here again, I have gone through and explained what everything was. My initial value is b, or my beginning, or y-intercept, you can call it that, but your initial value is where you're starting from. My rate of change, of course, is my slope. X is my independent variable, and y is my dependent, so the x and y stands for a lot of xy points on your line. All right, let's practice some word problems using this. So I have a town of 30,000 people, and it grows by 2,000 people every year. You could say per year. If P gives the town's population, then P is a linear function of time t measured in years, because the population is growing at a constant rate of 2,000 people every year. Okay? So what is the average rate of P over the time interval? Well, they just said it's 2,000 people per year. This line right here stands for per, and these are your 2 units. And I always tell you, if it purrs and it's not a kitten, then it's a rate. So this is a constant rate. Every year it's increasing 2,000 people per year. Okay? We're going to show a table on the next one how to do this, but let's figure out what a linear formula would be. Well, basically, the average rate of change, again, is your slope. So now I know my slope is 2,000 people per year. If my linear function, and we're going to find a formula for this, I'm going to do the table in the next one, is y equals b plus mx. We already know the slope is 2,000 people per year. So I've got the 2,000, and I can put the x there. What was my initial value? But if you look at your initial value, or your b, it's like how many people were in the town when it began, and they said 30,000 people. So I put the 30,000 right here. So if you look at it, y is 30,000, that's my beginning, plus 2,000 people per year. You just came up with a formula. But they want it in terms of p and t, so I'm going to change the y to population equals 30,000 plus 2,000 t. If they give you different variables, I don't care if you use the y and x's to come up with your formula, but I want you to write it the way they want it. So let's look at this on the next page to see how this would look. And I kind of have the graph here. So at the beginning, when time was 0, we had 30,000 people, and then every year it's increasing 2,000. So I'm going to go in time, years of 5, 10, 15, and 20. So you get more of a long-term thing. So if it's increasing 2,000 people per year, over 5 years it increases 10,000. So that's 40,000, and then 50,000, 60,000, and 70,000. Let's graph this to see what it looks like. So when year 0, here's my beginning, my initial value is 30,000. Down here it's 5 years down here, so it goes up to 40. Then 10 years it's 50. 15 years it's 60, and then it comes all the way up here to 70. See if I can get this all to show on the screen. And then I'm sure your line's straighter than mine. Let's draw a line through all these points, and there is my straight line. And if you look at it, look at the rate of change is this. See how it's constant here? So your slope is the same each time. For every 10,000 it goes up. That's another 5 years, which is your 2,000 people per year. Let's look at another problem. Before we do this next problem, I want to talk about straight line depreciation. And accountants use this all the time, where they depreciate, which means it loses money. And they call it straight line depreciation because it's a constant decline. So they call it straight line because it's a constant. So let's define this. It loses value at a constant rate per year until the value is 0. Now, accountants use this all the time. They'll have equipment and they'll put it on the books and they'll say, okay, every year the equipment's going to be worth less and less and less until it's a value of 0. There's a lot of places that have a lot of equipment on the books that are worth nothing, but they still use that. But that's what the tax code is they depreciate it down to 0. So we have a small business here. It spends $20,000 on new computer equipment and for tax purposes chooses to depreciate it to 0. Excuse me, at a constant rate of change over a 5-year period. Make a table and a graph showing the value of the equipment over the 5-year period. So first of all, it's $20,000 and we want to do it over 5 years, so we have to depreciate it to 0. So let's figure out our average rate of change. So we have $20,000 for the equipment over 5 years. That means every year we have to depreciate that $4,000 per year so that it'll reach 0 after 5 years. This is a typical way to do especially computer equipment because it depreciates and it really doesn't hold its value. Let's look at the table here. So this one goes the other way. At time 0 it was worth $20,000 and every year after that it drops $4,000, so we're down to $16,000, $12,000, $8,000, $4,000, and then we're down to 0. So we did a straight line depreciation. How would this look on our table? Well, it's 20 here. This is our beginning value, our initial value, down to 16, down to 12, down to 8, down to 4, and then it's down to 0. And again, your line will probably look a lot straighter than mine, but we just depreciated that down to 0. So after 5 years, that computer equipment is not worth anything. Example number 3. A woodworker goes into business selling rocking horses. His startup costs, including tools, plans, and advertising, total $5,000. Labor and materials for each horse cost $350. So we want to calculate the woodworker's cost to make 1, 2, 5, 10, 20 rocking horses, and we're going to sketch it. But before we do that, let's find a formula for this cost. And we're going to use C and N, but we'll use Y equals B plus MX. So if we were to do this, what's my initial cost to start? Well, it's $5,000, whether I sold a horse or not. And then for every horse, it's going to cost $350 for materials and labor. So my equation is 5,000 plus 350x. So I hope that this woodworker charges more than $350 per horse, or it's just not going to make any money because he has to pay back that 5,000 that he used to start up. But we can't leave it like that. We have to leave it in formula and it's C and N. So the cost is going to equal $5,000 plus 350 N. Now, what is the rate of change of the function C? Well, the rate of change, of course, that's changing is the $350 per horse. Notice I'm comparing two different units. What does the rate of change tell us about the woodworker's expenses? Well, it tells that it's going to increase each time, and so he's got to sell, like I said, his rocking horses for more than $350 to make money and to pay back his starting costs. We can go through and figure out the cost of this. I'm going to start this, and you can do this on your own, but at first it cost $5,000 for the total cost, and then after he did one horse, it went up to $5,350, 2 horses, we went up to $5,700, and so on and so on. I'll let you finish filling this in and do the table. You remember, I'll just get this started for you a little bit too, is that you can start at 5,000 and this is going to creep up, and it's going to be a straight line because its costs are increasing. So please continue with this and fill in this slide. Stop the tape if you need to. All right, let's talk about the general formula again. So this page I kind of made for you, where I've got the formula again here. I'm showing you slope, and the vertical intercept or the y-intercept is your b value. We call it your initial value or your starting point. So that's just to kind of summarize what we talked about today. I just have one last thing to say, is there's a warning. Not all graphs that look like lines represent linear functions. Make sure that you're looking at the entire graph, because sometimes when you graph something, make sure that your rate of change and your slope are constant. If I graph something and I only see this part of the graph that I'm showing you here, it looks like a straight line, but it really isn't the whole thing. So make sure that your window or your rate of change is constant for you to get an accurate picture of this.